the classification of metal. Yes. Let's see the classification of metal. First of all, now see before proceeding further, I will explain you few things. Like if you take a conductor, this will be very helpful for understanding the an entire chapter. Okay, if we take the conductor, let us consider that we are taking. If we take the conductor, let us consider that we are taking an iron rod. Okay, an iron rod. Okay, let us consider we are taking an iron rod with which we are connecting a battery, and if we are switching this battery on, this is a battery. If we are switching this on, if we are switching this on, then what will happen? Yes, current will flow. Current is flowing, that means what? Electron is flowing. Okay, now on the other side, if I consider an insulator, if I consider an insulator, then what will happen if I take an insulator? Let us consider that I am taking a plastic bottle. I am taking a plastic bottle. Okay, and if we are connecting it with a battery, what we will see, we will see that there is no flow of current. If there is no flow of current, that means what? That means there will be no flow of electron. See, in conductor, there was a flow of electron. In insulator, there will be no flow of electron. Now let us consider that we have a silicon. Let us consider that we have a semiconductor, and the most commonly used semiconductor is silicon and germanium. Silicon and germanium. Okay, these are group 14 elements. Okay, semiconductors are group 14 elements. Okay, remember the tricks of learning this thing. What can be used as a semiconductor? We can use silicon, we can use germanium, and group 14 elements. Group 14 elements can be remembered as Kahe Shivji Suno Parvati. Carbon, silicon, germanium. Then we have carbon, silicon, germanium, and this two will be mostly used. Okay, now let's see. Yes, for the case of semiconductor, I'm marking it with for the case of semiconductor, let us consider that we are considering a silicon material. I can make it more nicely. Yes, we are having a silicon material, and that silicon material is connected to a battery by means of a wire. by means of wire. Okay, by means of a wire. Then what will happen? Okay, if we are connecting the silicon with the help of wire, then what will happen? See, in this case, if it is in a normal temperature, the current will flow. That means electron will flow. But if we keep this setup in a fridge, there will be no current. There will be no flow of electron. See, this is a device. This is a thing which is sometimes acting as a conductor, and sometimes it is acting as an insulator. So that the thing which is sometime acting as a conductor and sometime acting as an insulator are known as nothing but semiconductor. Where it will be acting as a conductor, it will be acting as a conductor at room temperature. When it will be acting as an insulator, it will be acting at a room temperature at low temperature. Okay, it will be acting as an insulator at low temperature. Okay, so these are the three basic classification of conductor, that is metal, insulator, and semiconductor. Okay, now let's see what's there in our syllabus. See, first of all, now we must know these two things. We know what is the meaning of electrical conductivity, and we also know what is the meaning of resistivity. Conductivity means property of conducting electron, and resistivity means property of opposition of electron. Okay, so for the first case is metal. Metal means what? Metal means conductor. In the case of conductor, they have extremely high conductivity. If they are having extremely high conductivity, that means their resistance will be low. High conductivity, resistance will be low. What will be the conductivity? Sorry, what will be the resistivity? Resistivity's value will lie between the range 10 raised to minus 2 to 10 raised to minus 8 ohm meter. And the reciprocal of that, just the reciprocal of that is electrical conductivity. Electrical conductivity will lie between the range 10 raised to 2 till 10 raised to 8 Siemens per meter. S will represent Siemens. Siemens means inverse of ohm. Done? Now let's see further. Now what? Now we have a semiconductor. What about the semiconductor? They possess conductivity or resistivity that is in between that of metal or insulator. Yes, they possess conductivity or resistivity that is between metal and insulator. Okay, so what is the resistivity of semiconductor? It's from 10 raised to minus 5 till 10 raised to minus 6. And what about the conductivity? It is just the reciprocal of resistivity, so it will be 10 raised to 5 till 10 raised to minus 6 Siemens per meter. Okay, now we should see about the insulator. Now what about the insulator? In the case of insulator, you have the resistivity from range 10 raised to 11 to 10 raised to 19 ohm meter. And in the case of conductivity, we have a range from 10 raised to 11 to 10 raised to minus 19 Siemens, Siemens per meter. So these are the three things. We have metals known as semiconductor. We have metals known as conductor. Then we have semiconductor, and then we have insulator. Okay, I explained you what is that by making this diagram. Okay. Now what are the examples of metal? In the case of metal, we can consider iron, cobalt, and nickel. In the case of semiconductor, we can consider carbon, we can consider gallium, we can consider silicon. Okay, and the most commonly used semiconductor are silicon and germanium. And in the third case, in the case of insulator, we can consider plastic, we can consider wood. Okay. Yes, these are the examples of insulator in which there will be no flow of electron. That means there will be no flow of current. Okay, now why these things are acting like this? That means in conductor, why current is flowing? In insulator, why current is not flowing, and why in the case of semiconductor sometime it is flowing, sometime it is not flowing, why it is happening, that we will going to study in the next slide. And that is energy, that we will study in the energy band theory. Okay, energy band theory, it is also known as band theory of solid. Why this, that we will study in the next slide, and the next slide is about the band theory. Okay, now let's see few more things based on that. See what I've explained, that the example of semiconductor, the example of metals, everything is given here. Okay, now we are studying about the energy band theory. Let's see. Okay, band theory. Actually, this is band theory of solids. Okay, in many of the books, it is also written that it is a band theory of solid. Let's see each thing one by one. Okay, first of all, before explaining the band theory, I will explain you the base of this. Okay, now let us consider that you have a sheet of a semiconductor. Okay, it is very important. We are having a sheet of semiconductor, just an imaginary thing. Okay, we have a sheet of semiconductor. In that sheet of semiconductor, we have many atoms of that semiconductor, of that material. We have atoms, or we have many atoms of that semiconductor, like this. Okay, now what we are doing, we are just studying on the first one. Okay, I am just magnifying it. I am magnifying it. What you will see, we have already studied that in every element there will be a nucleus. Outside the nucleus there will be electron revolving around the orbit. Okay, electron revolve. There will be not only one orbit, there will be more than one orbit. Let us consider that we have a 3 orbit here. Okay, yes. First orbit, second orbit, and third orbit. Okay, now understand what we are going to see. See, we are plotting the energy band theory. Okay, in this there will be an energy. Okay, now what we are doing, we are taking one semiconductor element, we are studying about the first shell electron. Okay, the first shell electron energy will be known as, it will be known as, I am plotting this here. Then from again, from this one, from the second one, again we are taking the energy from the first shell. Again from the third one we are taking energy from the first shell. Again from the fourth one we are taking the energy from the first shell. Again from the fifth one we are taking the energy from the first shell. Okay, so just remember, when we are plotting the energy of the first shell electron, what we will get, we will get the first band. Okay, what is this, how I plotted this line? I am plotting the energy from first shell electron of entire element. What I will get, I will get first band. This is your first band. Okay, then what if I am plotting the energy of electron from the second orbit, then I will get second band once again. Okay. Yes. Now what? If I am plotting the energy from second shell electron, I'll get from second shell electron, I'll get second band. Okay. What is this? This is the energy of electron from second shell. Okay. Now, like this, if I plot, this will be your second band. Okay. Now, like this, if I plot the third shell electron energy, then what I will get? I'll get third band. Okay. I will get third band. Understand everything here? Yes, I'll get third band. Okay. Yes. If I am plotting the energy from the first shell electron, I'll get the first band. From second shell, I'll get second band. From third shell, I'll get third band. But if third one, see, if you are plotting, like example, if you are plotting the energy from the last shell, anyways, it will going to end. If we are plotting the energy from the last shell, then it will be known as valence band. I repeat again. First shell energy will be known as first band. Second shell energy will be known as second band. Third shell energy will be known as third band. Last shell energy will be known as valence band. Okay. And if in this case I am considering that the third shell is the last one, then I can say that this will be what? This third band will be what? It will be your valence band. It will be your valence band. Okay. If you're plotting last shell energy, then it will be known as valence band. Okay. See, the electron which is revolving in the orbit, that will not make current. The current will be made by the electron who will jump from this orbit to that orbit, from first orbit to second orbit, from second to third, from third to fourth, from fourth to fifth. Like this, the moving electron are responsible for making current, not the revolving one. Okay. So if I am plotting the energy of the electron which is moving, then that will be known as conduction band. It will be known as conduction band. Okay. I am plotting the energy of the free electron. If I am plotting the energy of free electron, then it will be known as conduction band. Okay. I repeat, just focus on my words. First shell energy will be known as first band. Second shell energy will be known as second band. Last shell energy will be known as valence band, and the free electron energy will be known as conduction band. And once again, listen to me. The distance between conduction band and valence band is known as forbidden gap. Okay, the distance between conduction band and valence band are known as forbidden gap, or you can say it as energy gap. The distance between conduction band and valence band is known as forbidden gap or energy gap. Forbidden gap or energy gap. Why I'm explaining you this story. This story is understanding is very important for understanding how the behavior of conductor, insulator, and semiconductor are different. Okay, now see what we are going to see. First of all, see first, if we have, let's say, first we have here conductor. So in the case of conductor, how that energy gap will look, your energy gap will look like this. Some. Okay, in conduction band, what will happen? See, valence band, lower one, and conduction band, upper one, they will overlap. They will overlap. If there will be an overlapping, then it will be known as conduction band. Okay. In the case of conductor, valence band and conduction band will overlap. Okay. Now let's see the next one. Next is insulator. In the case of insulator, the distance between valence band and conduction band is greater than 3 electron volt. I'll make valence band, I'll make conduction band. Okay. This is your valence band. We have this diagram further. Okay, yes, we have this diagram. Okay, yes, I'll show here. See. I explain you the conductor part. See, this is in this, if you see, valence band and conduction band, the energy gap between valence band and conduction band is greater than 3 electron volt. And in the case of semiconductor, the gap between valence band and conduction band is smaller than 3 electron volt. First it is greater than 3 electron volt, then it is smaller than 3 electron volt. Okay? Yes. Okay, now see what happens. In the case of conductor, there will be an overlapping. What is the meaning of overlapping? Overlapping means this shell will get overlapped to the another one. There will be overlapping. Okay, that means the valence band electron is converted into the conduction band electron. But in the case of insulator, the gap between the two atoms are quite high. And in the case of semiconductor, the gap between the two electrons, atoms, it will be moderate. If, see, in the first case we don't have to heat anything, but if in the second case, if we are not in the second case, in the third case, if we are heating, if we are heating if we are heating semiconductor, what will happen? Electron will get energy, and that electron will transfer to conduction band. Electron will get energy. See, why there is a gap. If electron gets 3 electrovolt, what will happen? Electron will gain energy. If electron will gain energy, it will move to conduction band. If electron is moving from valence band to conduction band, then what will happen? There will be a flow of current. Okay. Acha, if we are heating in semiconductor and we can transfer electrons, so why we can't do the same in insulator? If you are thinking, see, that's a valid question. But if you heat the insulator, the energy required is greater than 3 electrovolt. Okay, energy required is 3 electrovolt. If you are heating, we reached 3, but there will be no jumping of electron. Why? Because electron needs to cross this potential barrier. If we started heating that material, then what will happen? Then the material will get destroyed. Let's see that the consider your bottle. If you are heating just to make it a conductor, so before reaching to conduction state, that will be melted. What we are studying the band theory of solid. It will be no more solid then. Okay. Yes. Let's see each thing one by one. Okay, yes, we'll see the cases because the theories are not so important. See, the first case I explained in the form of diagram previously. Okay, a metal can exist when the valence and conduction band overlap. When the band is partially empty and the conduction band is partially full, the electron from valence band can readily migrate to conduction band when there is an overlap. There are lots of electron accessible for electrical conductivity in this scenario. Conduction is made feasible when the valence band is partially empty because electron can go from its low level to its high level. As a result, these materials have high conductivity and a low resistivity. Okay, now in the case 2, in this case, a significant band gap is present. Greater than 3 means it will be what? It will be insulator. Is present. Electrical conductivity is not feasible because there are no electron in the conduction band. Keep in mind that heat simulation cannot excite electron from the valence band to the conduction band due to the enormous energy gap in the case of insulator. Despite now the third case, already explained in this case. Yeah, despite they're small in this case, the band gap is tiny but finite. Some electron from the valence band can gain through energy at ambient temperature to cross energy gap and reach the conduction band because of the tiny band gap. These electrons can move in the conduction band. As a result, semiconductors have low resistance than insulator. Okay, yes.